Hello everybody. Now we will discuss the Laplace transform. I believe some of the audiences will not be familiar with this term, the Laplace transform term. So I will make this video as an introduction to Laplace transform to get an idea about Laplace transform and to practice Laplace transform on simple mathematical equations. So this is, I'll try my best to make this a simplified discussion that will deliver the message without missing any big parts of the figure. This topic is a big topic, and there are many details that I'm not gonna cover, and that's why I hope this will cover the part that we are interested in the course. So I just want to make it clear, because you might be interested in more details than you can find more in any mathematics textbook. So the Laplace transform, what we're gonna do with Laplace transform is kind of similar to what we do here. So this is what we do for any differential equation that is in the form of y dash equal f of t. So y dash is the first derivative of y with respect to t. So this is dy by dt, for instance. This is y dash. So this is a function. And y dash is a function of t. This function can be x, can be, or t can be t squared, can be ln t, can be exponential, sine, cosine, whatever the shape. It's a function of t, and t is the independent variable, y is the dependent variable. And what we do with these differential equations is we integrate them what we want to do is to do analytical integration to get the algebraic equation of y as a function of t. Y, not y dash, so the function itself. And this is what we did. If you remember what we did in chapter 24, we have already covered this many times to get the concentration as a function of location z or r or whatever. We start with the differential form, and then we integrate this equation with any mathematical means, but this is what we did before. So sometimes this analytical solution is difficult, either because the equation is tough, is difficult to integrate, or because the solution steps are long, or any other reason. Despite having a lot of tools like the integration methods, like the tables of integrals, we still have some functions that are difficult to integrate. So the thing that Laplace transform will offer for us is that it will allow us to do the integration without the need of going through all these integration techniques. So what we will do is we will convert this from convert the equation from its form in the time domain as a function of t into another domain, which is a function of s. So this is what we do. We do Laplace transform, which converts the function from the time domain into the s domain. The s is the variable that corresponds to t in the time domain, the actual domain. This is, you can consider this as another dimension where the function takes another form, which is simpler and more easy to deal with. So this this is, I believe, this is a genius mathematical way of doing this, because it makes the solution of the equations, and it's fantastically easy. It is very easy compared to what you do in the analytical solution. What we do is we do this transformation. We will understand how we do this transformation later, but let's say there is a method that we can use to transform the equation from the time domain into the s domain, so the equation is in a simpler form. This form, if it's a differential equation, it will turn out or end up here to be an algebraic equation. The d by dt disappears and is transformed into algebraic form, and this algebraic equation can be transformed into a simpler form, or get y as a function of s, and this y is got by simple algebraic methods. You add, subtract, you get common factor, you divide, and you get common denominator or whatever. They're all simple, very, very simple algebraic methods, like high school algebra thing. And this is what corresponds to the analytical integration in the time domain. So the analytical integration in the time domain is a simple algebraic solution in Laplace domain or in the S domain. And once we are done, this is the simplified form of the equation. You can return it back to the time domain by doing what we call the inverse Laplace transform. So this is the same solution that you get from here. You can get it by doing Laplace transform, simple algebraic solution, and then inverse Laplace transform. So just to make it into points, so Laplace transform is just a mathematical method that converts differential equations into algebraic equation, or converting ordinary differential equations into algebraic equations, or it can convert partial differential equations into ordinary differential equations. And this is why we discuss this in this chapter, because we will use Laplace transform to convert the ordinary differential or the partial differential equation into ordinary differential equations. The equations are primarily or originally in a function of time, t, and it's later converted into a function of s. And in the S domain, the equations are easier to solve. You just use simple mathematical methods, and once you're done, you use what we call the inverse Laplace transform. So when we do Laplace transform, how we do this transformation from the time domain to the S domain, it's done using this formula, which is the Laplace of function of t is what we call the f of s, the integral of exponential of minus st f of t dt. And of course you might feel upset now, because this is gonna make life difficult now. How can I do this integration for my function? It's easier to do the regular integration for the function that I have already. But just to make you like happy, this is not what we're gonna use. There are already some tables like what you see here. These tables are available for many functions. For each function, you see how it looks like in the S domain and how you transform it into the time domain. So you don't need to do this integration. It has already been done for a lot of functions, so you don't need to bother yourself. Just go to the tables, see what's the function in time domain, what's the function of S domain, go back and forth between them, and that's all. There are many of these functions, and I'll put a table in the a link to a table in the description of this video for a table of integrals. I'm sorry, it's table of Laplace transforms. It's I think 130 something or 140 something transformations. So they're available. You can see there are like big variety of functions. But let's take a look. One of them, or these three, are the ones that I believe are interesting, which is the first derivative in the time domain is converted into s multiplied by f of s minus f of 0. So this is the derivative, and you see here, and this is the beauty of Laplace transform. You see it's converting this from a differential form into an algebraic form. Even the second derivative, it's converted from a differential form into s square and s, and that's it. F of n, if it's like fourth derivative, fifth derivative, whatever the derivative, you can get it into an algebraic form, and this is the magic of Laplace transform. So you can see how impressive is this. So still I believe things are not clear now, but we can do this on an example of a function that we are familiar with. So let's say I'm gonna solve this equation, which is a second derivative of y with respect to t minus 16 multiplied by y equals 0. This is the equation in the time domain. We know the boundary conditions that y at time equals 0 equals 1, and the first derivative at time equals 0 equals to 1. And we have here some useful Laplace transforms that we will use. So I picked them from the table because these are the functions that we are gonna be using here. So now let's take it step by step. First, we need to define what we mean by f of s and what we mean by f of t. F of t, let's take it as f of t first. F of t is the parameter that is dependent on time. If you take a look at this equation, t is the independent variable, y is the dependent variable. So y is dependent on time. So f of t is y. And if you're gonna put it in the Laplace transform, I'm gonna call it f of s. So if it's f of t, then it's the uppercase f of t. It's the Laplace. I mean the function in the time domain. And if it's lowercase f of s, it's the function in the s domain. Now let's see how we can transform the boundary conditions. For instance, I have y at t equals 0, so y is f of t at t equals 0, then it's f of 0. So this is f of 0 equals 1. And this is f dash of 0 equals 1. So these are the boundary conditions that I have. And now let's see how the function looks like. The function will look like this. It's the second derivative, which is f double dash of t, minus 16 multiplied by y, which is f of t, is 0. Now let's take a look at the table. What is the transform of this f double dash? You'll see it's s square multiplied by f minus s multiplied by f of 0 minus f dash of 0. And f of t will be transformed into f of s. This is how we transform it. So this is the equation. Now see, this is the equation, and we have here the two boundary conditions are already part of the equation, and this is impressive. If you remember how we use the boundary conditions, you do the integration, you put constants, and then you substitute with the first boundary condition, with the second boundary conditions, get two equations and two unknowns, and solve them, and do all these steps just to get the constants or to use your boundary conditions. Now you don't need to do all this. You just put the boundary conditions as part. These are the boundary conditions. F of 0 and f dash of 0 are the boundary, or in this case will be the initial conditions. So these are the initial conditions that I have. And I know f of 0 and f dash of 0 both are 1, so this is the equation after applying the boundary conditions. It's now an algebraic equation. You can see how easy you need to deal with it. All what I need to do is to get f of s as a function of s. This is all what I need to do now. So to get the f of s as a function of s, I'll just take common factor, divide by this thing here, the s square minus 16. It's very simple algebra. So it's s plus 1 divided by s square minus 16, which is s plus 4 multiplied by s minus 4. And I want to tell you that at this step I'm done with the integration. You can imagine that here we are done with the integration and the function is integrated. I mean, what I did now is corresponding to the integration in the actual time domain. So it's very easy. And now what I need to do is to look for a shape of this equation in the table so that I can get the inverse Laplace of it. Unfortunately, you will not find this shape, but the closest things that you will find are these two cases: 1 over s minus constant or 1 minus s plus constant. This can be put in a form of 1 over s plus 4, or a constant divided by s plus 4 plus constant divided by s minus 4. Just simply because it's an addition of two fractions, and then you got the common denominator. So you're inversing the process. So I'm saying that this is equal to a over s plus 4 plus b over s minus 4. Multiply everything by s plus 4 multiplied by s minus 4. So this is what you get: s plus 1 equals a multiplied by s minus 4 plus b multiplied by s plus 4. Again, I'm just doing simple algebra. You want to get the value of a and b, you get the coefficient of s and the constant. At the right hand side equals to the left hand side, and these are the two equations you have. Get the value of a and value of b, you find 5 over 8 and 3 over 8. And this is the equation that you have. It's 3 over 8 divided by s plus 4 plus 5 over 8 divided by s minus 4. Now these are constants, so they're not gonna make any difference with the transform, but this is 1 over s plus 4 and 1 over s minus 4, which are these two cases. So they're gonna be exponential of at and exponential of minus at. So this is the simple inverse Laplace transform of this is gonna be 3 over 8 exponential of minus 4t plus 5 over 8 multiplied by exponential of 4t. It's very simple and straightforward. Now let's see how we can do this in the actual process. If we are not using Laplace transform, we can do this by doing the integration. We see that this is this case, it's the same case we did before. We can pick the exponential form here. So it's gonna be C3 multiplied by e power 4t plus C4 multiplied by e power minus 4t. If you look at the solution that we just got, there is exponential of minus 4t and exponential of plus 4t. So we're getting close, but now we need to get the constants, and to get the constants we substitute with the first boundary condition and then get the derivative to get the second boundary condition, substitute each time with t equals 0, and then you get two equations and two unknowns, and from these two equations you get C3 and C4, and you get the exact same equation that we got using Laplace transform. So this is very simple way of doing the integration, and it is giving us the same output as the case of analytical solution. There are some cases of the equations where we don't see this the equation in the table. For instance, if I have an equation like this that we see here, in this case we don't have it in the table, and the integration of this is going to be very tricky. So Laplace transform will help us do the integration like very simply. So we'll follow the same procedure. We will put the boundary the equation in this form. We will use the boundary conditions. F of 0 is 1 and f dash of 0 is 0, and then do the Laplace transform of the equation. This is the second derivative, s square of fs minus sf of 0 minus f dash of 0, and the same for 3 multiplied by this, which is this, plus 2 f of s, which is the Laplace of f of t. We know that f dash is 0, so this is gonna be 0, this is 1, this is 1, so you can substitute with the boundary conditions. We can rearrange the equation, get it in a simplified form, and this is the form of the equation. We'll do the same thing, get common return it from the common denominator to two separate fractions or summation of two fractions, get the value of a and b, and we're done. This is the integration that we have of this equation. So it's very helpful actually. It's a very helpful tool that we can use. So I'll stop here, and in the next video we will talk about some more mathematical concepts that we need to understand and know before we start talking about the mass transfer in unsteady state conditions and the cases that we will cover in this chapter. So I'll see you next video, inshallah. Goodbye.